Welcome to the world of Klingelnberg drive technology, where precision gear manufacturing reaches its zenith. Gears might seem simple, just toothed wheels, but creating them to modern standards is extraordinarily complex. What you're watching is the complete production cycle of precision gear components. It starts with gear hobbing, where a specialized cutting tool called a hob gradually machines teeth into a rotating blank. Think of it like cutting threads on a screw, but vastly more complex. The hob and workpiece rotate in precise synchronization, with the hob feeding across the blank to cut each tooth profile. Klingelnberg's technology shines in the finishing process. After initial cutting, gears undergo heat treatment to harden them. But here's the challenge. Heat treatment causes slight distortions. That's where gear grinding comes in. Using special grinding wheels, the system removes just thousandths of an inch of material, correcting those distortions. This is the SIMASV horizontal pipe bending machine, tackling one of the tougher challenges in metalworking, bending large diameter pipe without collapsing, wrinkling, or deforming it. The SIMASV uses horizontal orientation and a mandrel system. That's a support that goes inside the pipe during bending, preventing the walls from collapsing inward. The bend happens progressively, not all at once. What's impressive is the control over bend radius and angle. The machine's hydraulic systems provide smooth, consistent pressure throughout the bend. This is heavy industry work that requires both brute force and a delicate touch. This is the Heusler VRM 4-roll plate bending machine, and what it's doing here would have taken crews of workers' days to accomplish just a few decades ago. Bending heavy steel plate is one of those jobs that looks simple but requires tremendous force and precision. The VRM uses 4 rolls working in perfect coordination. The material passes between these massive rollers, each precisely positioned by computer control. What makes this machine special is its multi-axis capability. It can create complex curves, not just simple cylinders. Watch how smoothly that thick plate bends without wrinkling or deforming. The hydraulic system generates hundreds of tons of pressure, yet it's controlled with fingertip precision. This is the kind of equipment that shapes the hulls of ships, pressure vessels for refineries, and large industrial tanks. The craftsmanship is now in the programming and setup. Folks, what you're about to see is one of the most fundamental processes of modern civilization, the transformation of raw iron ore into the steel that builds our bridges, our buildings, and our automobiles. It all starts with iron ore, essentially rock containing iron oxide, and coke, which is purified coal that's been heated to remove impurities. First, let's talk about the blast furnace you're seeing here. This massive structure can stand over 100 feet tall and operates at temperatures exceeding 3,000 degrees Fahrenheit. The process begins when iron ore, coke, and limestone are loaded into the top of the furnace. Gravity does its job, pulling these materials downward. Meanwhile, superheated air, we call it blast, which gives the furnace its name, is injected from the bottom. This creates an incredible updraft of heat. As the coke burns, it produces carbon monoxide, and here's where the chemistry gets interesting. That carbon monoxide pulls the oxygen right out of the iron ore, leaving behind molten iron. Watch as the molten iron collects at the bottom of the furnace. It's glowing that brilliant orange yellow because it's around 800 degrees Fahrenheit. The limestone we added earlier has combined with impurities to form slag, which floats on top of the heavier iron. This slag actually serves as an insulating blanket, keeping the iron molten. When it's time to tap the furnace, workers drill through a clay plug at the base. Out flows the liquid iron in a spectacular stream, channeled into refractory-lined troughs. This is called pig iron, and while it contains about 95% iron, it's still too brittle for most applications. The next step is the basic oxygen furnace, where pure oxygen is blown through the molten iron at supersonic speeds. This removes excess carbon and other elements. The beauty of this process is its control. By adjusting oxygen flow and adding precise amounts of other metals like chromium or nickel, steel makers can create hundreds of different steel grades, each tailored for specific purposes. Finally, the molten steel is cast into enormous ingots or continuously cast into long slabs. Some of these facilities can produce over 500 tons of steel per hour. It's the same fundamental process that built America's Industrial Revolution, just refined to incredible levels of efficiency and precision. Now, if you've ever wondered how those intricate metal parts in your car engine or airplane are made with such incredible precision, you're looking at the answer right here. This is Mastercam 2020, one of the most sophisticated computer-aided manufacturing systems in the world today. What we're witnessing is optical milling, a process that combines the time-honored tradition of milling with 21st-century computer precision. Back in the day, machinists relied entirely on their eyes, their experience, and their steady hands. Today, Mastercam takes that human expertise and amplifies it 1,000-fold. Here's how it works. First, engineers create a three-dimensional digital model of the part they need. Think of it like a blueprint, but instead of paper, it exists in the computer. Mastercam then calculates the exact tool paths. That's the route the cutting tool will follow, down to tolerances of just a few thousandths of an inch. That's thinner than a human hair. Watch as the machine positions the workpiece. The optical system uses high-resolution cameras and sensors to verify the exact position of the material before any cutting begins. This is crucial because even a microscopic error at the start can ruin an entire part worth thousands of dollars. Now the milling begins. That spinning tool you see is removing material at incredibly precise depths. The beauty of Mastercam is in its simulation capability. Before the machine ever touches real metal, the software has already run through the entire process virtually, catching potential problems. The cutting fluid you see flowing keeps everything cool and washes away chips. What's remarkable is how this technology preserves the essence of traditional machining, while achieving precision that would have seemed impossible just a generation ago. The result? Parts that fit together perfectly, every single time, whether it's the first piece or the 10,000th. Here's something that beautifully bridges the ancient art of glassmaking with modern automation: the glass forming machine 5406. The process starts with molten glass, heated to approximately 100 degrees Fahrenheit, being fed into the machine as a continuous ribbon of glowing, viscous material. The Model 5406 is what we call an individual section machine, or IS machine. It can have multiple sections working simultaneously, each independently forming glass containers. First comes the settle blow, where compressed air pushes the glass into the mold's shape. Then the blank mold opens, and the partially formed piece, called a parison, is transferred to the blow mold. Here's where the magic happens. Compressed air inflates the parison from the inside, pressing it against the cooled mold walls to create the final shape. The cooling has to be carefully controlled. Cool too fast, and the glass becomes brittle. Too slow, and production grinds to a halt. And finally, we're witnessing pure cutting power. The Irmoxon FiberMac 8 kilowatt fiber laser slicing through 35mm mild steel plate like it's butter. Fiber laser technology represents a quantum leap from the old CO2 lasers some of you might remember. The 8 kilowatt rating refers to the laser's power output, enough concentrated energy to vaporize metal instantly. Watch that brilliant light at the cutting point. That's steel being turned to gas and molten droplets, blown away by high-pressure assist gas. What makes fiber lasers special is their efficiency and precision. The beam is incredibly focused, narrower than a pencil lead, allowing for intricate cuts with minimal heat-affected zones. Now here's something special. The handcrafted production of Graf von Faber-Castell fountain pens, where old-world craftsmanship remains absolutely essential. Despite all our modern technology, this German company has been making fine writing instruments since 1761, and they haven't forgotten how it's done. The barrel and cap are hand-polished through multiple stages. This can take hours for a single pen. The nib, the business end of any fountain pen, is perhaps the most critical component. Made from gold alloy, each nib is individually shaped, then hand-ground to create the precise flexibility and ink flow characteristics. Assembly requires steady hands and careful attention. Each component must fit precisely, yet move smoothly. The final testing involves actually writing with each pen, making minute adjustments until it performs flawlessly.